Have you ever pondered over the role of world models in shaping modern technology? These ingenious representations are like the mind's eye for our machines, giving them a sense of understanding about the environment they interact with. World models are at the heart of numerous technological fields, from artificial intelligence that can comprehend and predict complex scenarios, to robotics that can navigate and manipulate their surroundings with precision. They play a pivotal role in simulations too, allowing us to create virtual environments that mirror the intricacies of the real world. World models are, in essence, the bridge between raw data and meaningful interpretation. They enable our technologies to perceive, predict, and interact with the world in a way that is both intelligent and adaptive. So, let's embark on this journey to unravel the intricacies of world models, to appreciate their profound importance and to uncover their boundless potential. Join us as we delve into the fascinating world of world models. What exactly is a world model? A question that might seem complex at first, but it's actually quite straightforward when you break it down. A world model, in essence, is a cognitive framework or mental representation that an artificial intelligence system uses to understand, interpret, and interact with its environment. It's like a map of the world, but not just a geographical map. This map includes information about objects, relations between objects, and the laws of physics that govern these objects and their interactions. Now, you might be wondering, why do we need these world models? Well, they serve a crucial role in helping AI systems make sense of the world around them. Just like humans use their understanding of the world to predict outcomes and make decisions, AI systems use world models to predict future states of the environment and decide on the best course of action. But let's delve a little deeper. How are these world models represented? In the realm of AI, a representation is a formal system for making explicit certain entities or types of information. And when it comes to world models, the representation could be symbolic, where objects and their properties are represented as symbols, or subsymbolic, where information is represented as patterns of activation across a set of units, like in a neural network. Moving on to the different types of world models, we have physics-based models, data-driven models, and hybrid models. Physics-based models, as the name suggests, are based on the laws of physics. They predict the future state of the environment based on the current state and the physical laws that govern the environment. On the other hand, data-driven models learn from data. They observe the environment, learn patterns, and use these patterns to predict future states. But what if we could have the best of both worlds? That's where hybrid models come in. These models combine the strengths of physics-based and data-driven models. They use the laws of physics to guide the learning process and make predictions, but they also learn from data to adapt to changes in the environment that cannot be captured by the laws of physics alone. So, to sum it all up, a world model is a mental map that an AI system uses to understand and interact with its environment. It could be represented symbolically or subsymbolically, and it could be physics-based, data-driven, or a hybrid of both. With this foundation, it's time to dissect the key components of world models. Like any complex system, world models consist of several crucial parts. Let's venture into the heart of world models and explore these pivotal components: the observation model, the transition model, and the reward model. Each of these parts plays a unique role, and together, they form the intricate, functioning whole of a world model. We'll start with the observation model. You can think of this as the eyes and ears of the world model. It's through this component that the model perceives its environment, taking in raw data and translating it into a form that the model can understand and use. In the realm of artificial intelligence, this might mean processing visual data from a camera feed, audio data from a microphone, or even more abstract data, like user interactions on a website. Through the observation model, the world model gains a snapshot of the current state of the environment, forming the basis for everything that comes next. Next, we have the transition model. If the observation model is the eyes and ears, the transition model is the brain. This is the component that takes the snapshot from the observation model and uses it to predict future states of the environment. For example, in a robotics application, the transition model might use sensor data to predict how an object will move, or how a terrain might change. This predictive ability is crucial for planning actions and navigating the world. The transition model is all about understanding the dynamics of the environment and forecasting what's to come. Finally, we arrive at the reward model. This is the component that evaluates actions and guides the world model's behavior. You can think of the reward model as a sort of internal compass, steering the world model towards actions that are likely to result in positive outcomes and away from those that aren't. In a video game, for instance, the reward model might encourage the AI to seek power-ups and avoid enemies. It's the reward model that imbues the world model with a sense of purpose and direction, driving it to interact with the environment in meaningful ways. Now, these components don't exist in isolation, they're interconnected, each influencing and being influenced by the others. The observation model feeds data to the transition and reward models. The transition model uses this data to predict future states, which in turn inform the reward model's evaluations. And the reward model's evaluations guide the world model's actions, which then affect the future states that the observation model will perceive. This cycle of perception, prediction, and evaluation is the engine that powers a world model. It's a dynamic, ongoing process, with each component constantly updating and adapting based on new data and feedback. It's through this process that world models are able to learn, grow, and navigate their environments with increasing sophistication and nuance. In essence, the observation model gives a world model the ability to perceive, the transition model gives it the ability to predict, and the reward model gives it the ability to act purposefully. Together, they form a holistic system, capable of understanding, interacting with, and learning from its environment. They're the nuts and bolts that make world models tick. Understanding these components brings us closer to grasping how we train world models, and that's our next stop on this journey. So stay tuned as we dive into the fascinating world of training world models. Training a world model is a meticulous process, and it starts with data collection. Like a seasoned artist gathering paints for a masterpiece, the world model requires data to paint its understanding of the world. This data could come from various sources such as sensors, databases, or even real-time user interactions. The key is to gather data that is representative of the environment the model will be interacting with. Once we've gathered our data, the next step is pre-processing. This is where we clean, normalize, and format our data to ensure it's in the best possible state for our model to learn from. Think of it as preparing a canvas, removing any imperfections, ensuring it's the right size, and priming it for the paint. Now that our data is ready, we can start training our model. This is where the magic happens, where our world model starts to learn, to understand, to predict. Two fundamental techniques are used in this process: reinforcement learning and unsupervised learning. Reinforcement learning, as the name suggests, is about reinforcement, about learning through trial and error. The model interacts with its environment, taking actions and receiving rewards or penalties based on the outcomes. Over time, the model learns to make decisions that maximize its rewards. It's like teaching a dog new tricks: reward good behavior, discourage bad behavior, and eventually the dog learns what to do. Unsupervised learning, on the other hand, is a bit more free-spirited. Here, the model learns by finding patterns and structures within the data on its own, without any explicit instruction. It's like giving a child a box of Lego bricks and letting them explore and build without any set instructions. Training world models, however, is not without its challenges. One of the key challenges is the trade-off between accuracy and complexity. A model that is too simple may not accurately represent the world, while a model that is too complex may overfit the data and perform poorly on new, unseen data. Balancing this trade-off is like walking a tightrope. Lean too much to one side, and you'll fall off. Another challenge is dealing with uncertainty. The real world is full of uncertainties, and predicting future states can be tricky. But by using techniques like Bayesian inference and probabilistic models, we can account for this uncertainty and make more robust predictions. Training world models is a journey, a delicate dance of data collection, pre-processing, and learning. It's an art and a science full of challenges and trade-offs, but when done right, it's a powerful tool that can transform the way we understand and interact with the world. Now, let's explore where these world models come into play. World models have a myriad of applications, from robotics to gaming and beyond. Let's delve into these fascinating realms, shall we? In the field of robotics, world models play a pivotal role. They enable robots to navigate complex environments, manipulate objects with precision, and exercise control in dynamic situations. A robot equipped with a robust world model can comprehend its surroundings, predict how changes will affect its future state, and determine the best course of action. For instance, we've seen robots that can effortlessly sort recycling, prepare a cup of coffee, or even perform delicate surgical procedures, all thanks to the power of world models. Now let's switch gears and step into the world of gaming. Here, world models are used to create intelligent game AI that can adapt to players' actions and provide challenging gameplay. They also aid in procedural content generation, where game environments are dynamically created based on certain rules and algorithms. This leads to unique and engaging player experiences every time. Remember that game you couldn't put down because each level felt fresh and exciting? Yep, you can thank world models for that. Lastly, let's venture into the realm of simulations. World models are crucial in creating virtual environments and training scenarios. They enable us to simulate real-world conditions in a controlled environment, allowing for safe and efficient testing. From training self-driving cars to predicting the spread of diseases, world models have made significant contributions. Throughout these fields, we've seen numerous success stories and breakthroughs. Robots that learn to navigate new environments faster than ever. Games that offer an unprecedented level of immersion. Simulations that accurately predict real-world outcomes. These are just a few examples of how world models are shaping our world. Having seen these applications, you might be wondering what's next. We've traveled quite a distance exploring the realm of world models. It's a journey through the intricate labyrinth of how artificial intelligence perceives, predicts, and evaluates the world around it. We've delved into the core components of these models, the observation, transition, and reward models that form the backbone of this system. We've seen how they work in unison, creating a holistic view of our environment, whether it's a robotic arm navigating a factory floor, or a game AI creating new, exciting worlds for us to explore. The importance of world models cannot be overstated. They are the bridge between raw data and meaningful interaction. They transform numbers and pixels into a coherent understanding of the world, enabling AI to react, adapt, and learn from its environment. This is the magic of world models. They turn code into cognition, algorithms into awareness. Yet, as much as we've covered, this is only the beginning of a much larger journey. The world of world models is vast and ever-evolving, with new techniques and technologies constantly emerging. Variational autoencoders, recurrent neural networks. These are just a couple of the algorithms that power these models. Each offers its own unique approach to learning and representation, and delving into these algorithms can provide valuable insights into the workings of world models. But why stop at learning? Why not take the leap and start experimenting with building your own world models? It's a challenge, no doubt, but one that offers immense reward. There's something profoundly satisfying about crafting an AI that can understand and interact with its world, about seeing a machine learn and adapt in ways that mimic our own cognitive processes. So, take the plunge. Dive deeper into the algorithms that power these models. Experiment, build, learn. It's a journey of discovery, of innovation, and of understanding. It's a journey into the very heart of artificial intelligence. Thank you for joining this exploration of world models. Remember, the world is but a model waiting to be understood.